Up next, we have brightness in cinema. When is it too bright? And our presenter today is going to be Stelios Plumis. And he received his Bachelor of Science degree in computer science from the University of Piraeus in Greece, and his master's degree in electrical and computer engineering from UBC in Vancouver. And he's currently a grad student at UBC pursuing his PhD and is an intern at Barco and MTT Innovation in Vancouver. His research interests include HDR technology, adaptation of HDR content to legacy SDR displays, perceptual studies, and video and imaging displays. So please welcome Stelios Plumis.
Thank you for the introduction. Hello, everyone. My name is Stelios Plumis, and today we're going to talk about brightness perception in cinema, and more specifically, when it gets too bright. The upcoming cinema technologies, we believe that they will support higher peak luminance values, as well as higher full-screen white levels, or average light. These are amazing, but there are growing concerns in cinema industry that any potential misuse of these capabilities might lead to visual discomfort for the observers. Why? Because they might disturb the adaptation process of the human visual system. Here we see the capabilities of our eyes, who can perceive light ranging between 10 powered minus 6 to 10 powered 8, or in other words, 14 orders of magnitude. However, at any given time, we can get adapted to only 5 to 6 orders of magnitude. And this adaptation mechanism is optimized for slow and gradual changes in the lighting condition of the environment. So any abrupt change, it really challenges this mechanism, and it creates the visual discomfort in the form of soft burning, feeling in the eyes, or we blink too much. So to take it to our environment, in any cinema auditorium, the adaptation level is being determined by the light on the screen as well as the ambient illumination. So we're going to think that the ambient illumination is really low, close to zero, so the light on the screen is a major player there. The current cinema, the operational range is between 24 millinits and 48 nits, as you all know. And if we think about the extreme scenario that we expose viewers to a black frame that is followed by a white frame, the jump in adaptation is almost 3 orders of magnitude. With the upcoming cinema display technologies, we don't exactly know the capabilities yet, but we believe that they're going to go way lower in darks, way higher in bright. So on the same example, going from black to white, the jump is quite greater. So we know out of studies that they conducted in a home environment that the reproduction of high luminance levels out from displays, they could lead to visual discomfort for the observers. However, there are great differences between home and cinema, like the field of view, the distance from the screen, the size of the screen, ambient illumination, of course, all of these, they affect the brightness perception. So in this work, we want to assess viewers' tolerance to temporal brightness transitions in a cinema environment. And why to study specifically the brightness transition? Because we believe that this is the case with the highest probability to cause visual discomfort. On the background, most of the studies that they are related to brightness perception out of a display, they focused on assessing the peak brightness preferences or the average preferences. And all of them, they were based in fall, like the average light in the screen. And they tried to correlate the fall value with the observer sensation. Here, we see a table. On the rows, we have ambient illumination levels. And on the columns, we have different field of view values. I'm going to start with the first related research to our work. The authors here, they assessed the viewer's brightness preference for natural images, and they concluded that any content with fall greater 130 candelas per square meter, provided no gain. Next, the authors here, they studied the relationship between high luminance values emitted by a display and the perceived discomfort glare. And they concluded that viewers, they reported the glare, to see the glare for fall greater than 164. In this study, the authors, they explored the physical reaction, what happens to our eyes when they get exposed to high luminance values. And they reported that higher luminance values emitted by a display, actually, they are related to reduced blinking, which is related to visual fatigue. So driven by these results, they suggested to limit the fall of the content to 125 candelas per square meter. And this work, this is most related to us. The authors here, they assessed the tolerance of viewers to brightness transition for a TV environment, and they reported transitions from 5 to 80, as well as from 10 to 160 as slightly annoying, and as annoying, transitions from 5 to 10 to 320. So they suggested to limit the fall for TV content between 10 and 80. And here, we see the actual cinema operational range. So cinema ambient illumination should be really low, close to 0. And according to SMPTE, we are between 33.3 and 61.8. On this green box, we see only one study, and they actually studied full-screen white frames, so still images. To get a better understanding about our limitations there, we conducted perceptual studies. Actually conducted 4 different subjective experiments where we assessed viewers' tolerance levels to brightness transition, and on these experiments, we also assessed the impact on these tolerance levels of the average light on screen, or the fall value, the peak luminance, the light distribution, as well as the color. All of these experiments, they had some common element. We were exposed viewers to transitions between the reference frame and the test frame. A reference frame stayed on screen for 7 seconds to give enough time for the observers to get adapted, and test frame only 1 second. After each transition, we asked viewers to tell us how much annoying was, and they had 4 options: comfortable, slightly annoying, annoying, and very annoying. Here we see the full values for the 2 types of frames. For the reference, the full value was 0.11 or 10, and for the test frame, the full value was ranging between 25 and 250. Here is our physical setup. We had an almost 4-meter screen with unity gain, and the observer placed 3.3 meters away from the screen, which was forming a FOV of 61.8. We made the decision to study this extreme case, so basically the first row in the cinema, because we knew that if we cover this one, it also will cover the cases with a smaller field of view. The ambient illumination, when the projector was off, we measured it to 0.1 lux, and we used the Barco DP4K 20 LHC as our main projector, which on this setup, we had a maximum luminance of 500 and a minimum luminance of 0.1. So our first experiment was the full color experiment. So we exposed viewers on brightness transition between color frames and white frames. And the main goal for this one was to really assess, in terms of fall variation, the minimum fall variation that lead us to visual discomfort. And of course, the second one, we wanted to see if this fall variation or jump in fall was consistent between white and colors. Please keep in mind that the reference frame and the test frame on this experiment was always the same color. So from red to red, from green to green, from white to white. And this is how we showed the actual color frames to the viewers. So we were blocking actually the two channels out of the white patch. So this is an example when we had the 20 candelas per square meter white. The red actually was 4.6, green 13.8, blue 1.6. In this experiment, we had 21 participants. Here we see the results when the reference frame was equal to 0.1. 0.1 also was the black level of the projector. So in that case, all the reference frames, no matter the color, were shown as black frames. For any group of bars, the red bar shows the transitions from red to red, from the green one from the reference green to the test green, blue from the reference blue to the test blue frame, and black from the reference white to the test white. What is really interesting here is that we see that for any group of columns, the actual light values, they are different between colors and as well colors and white. However, the annoyance level for the transition from 0.1 to these 4 cases is almost the same. That makes us to believe that visual discomfort is only influenced on a color basis. So, or in other words, if a given type group of cones blitzes, it leads to visual discomfort. Another interesting point is if 2 groups of cones blitz at the same time, so here, here we have the green that is obviously close to blitz, and also the blue. And when they blitz together, in the case of white, we don't see a greater visual discomfort. It remains the same. So the results, they are coherent with, if we think about the peak sensitivities of our human vision on the primary colors. Here we see the results when we raise the fall of the reference frame to 1 candelas per square meter. And it's interesting that we don't see almost any variation. It's the same threshold as we had when the fall level was 0.1. However, the annoyance levels, they drop significantly when the fall of the reference frame is raised to 10 candelas per square meter. So here we have a sum-up table for only the white transition. And here we have the fall for the reference and the fall for the test. With green are these jumps that they were rated as comfortable. With orange are the ones that they rated as slightly annoying for some of the observers. Yellow, the ones that they rated as slightly annoying for most of the observers. Gray, annoying for some of the observers, and red, annoying for the average observer. What we can say that there is a given jump in fall that will lead to visual discomfort. And by raising the fall of the reference frame, we also raise the threshold that the annoyance becomes a reality. However, for some given luminance levels, no matter the reference frame, they're still annoying. And we believe that happened because the contrast between the screen and the ambient light was really high. So we believe that these 2 cases, they were annoyed by themselves. Regarding color, as I said before, our results, they show that visual discomfort can be driven even from only 1 cone of types. If only 1 blitz, then viewers, they experience the discomfort. So on the first experiment, the distribution of light was uniform. However, this is not the case for the actual cinematic content, right? And we wanted to see how the results gonna change if we study the cases when the light is concentrated on small area or highlights. So this experiment and all the followings, we did them only in achromatic content since we already established the relations between color and white on the first experiment. And for this one, we had 17 subjects. So here we see an example. The reference frames, they remain the same as the first one, and the same, like obviously only gray, and the same fall values, 0.1, 1, and 10. But the test frame now, it was a black uniform frame with square highlights. And we processed these frames in order for this one, the fall level is 35 candelas, and we chose the peak luminance to be 10 times the fall level, so 350. In order to justify the fall and the peak relationship, the highlights ratio, they were covering only 10%. Here we see another example of another test frame, fall exactly the same as before, 35, peak 2 times the fall, So in order to have these two, the highlights, they had to cover 50% of the screen now. This is a table with all the combinations between fall and peak luminance values. For some of them, we couldn't do them due to projector limitations because, as I said before, the peak luminance of the projector was 500 candelas per square meter. Here we see the result. For any given group of columns, of bars, the blue is when the peak is 10 times the fall, the orange when the peak is 4 times the fall, the yellow peak 2 times the fall, and purple the results from the experiment 1. So this is the case when the fall level for the reference was 0, 0.1. So again, it was actually black. What we see here is that light distribution has minimum impact to viewers' tolerance. And this is something that we also see when we raise the fall to 1 candela per square meter for the reference frame. And obviously, it's something that propagated when the fall is raised to the 10 candelas per square meter. As a takeout of this experiment, variation of fall so far seems to have the strongest impact on viewers' tolerance in brightness transition. Not the peak luminance, not the contrast, and not the light distribution. So far, we had only patterns, basically, test patterns. So we wanted to see if we're going to get the same result when we have something closer to the actual content. So we replaced the test frames with the square highlights with noise frames. And why noise frames? Because they have light distribution really close to actual content, and also they lack details, context, and edges or whatever that they can attract the viewer's attention, and they might alter the result. Reference frames, they stay the same as before for consistency reasons. And here we see our noise frame that we created by combining the background of 30 images. And this is another example when we process this noise frame to have exactly the same fall value in the same time, but the peak to be different. This kind of processing introduced a lot of contrast inequality that might alter the result. Here are the results. It's a similar way of presenting as the previous experiment. Please note that the purple shows the results from experiment 1, uniform white to uniform white. And this is the case when the fall level of the reference was 0.1. And actually, we see not a great change from when we had just the square highlights. Again, distribution of light and peak luminance and contrast, they seem to have almost no effect on viewers' tolerance to brightness transition. And we also see some slight trend that may be transitioning to frames with really small and bright highlights might be less annoying than going to a full screen white frame for the same fall value, but it's really light. Statistically, it's not significant. And these are the results that they propagate also on the next, when we raise the fall of the reference to 1 candela, and also when the fall of the reference is 10 candelas per square meter. So we get similar results as before. So as I said, fall seems to be the main contributor on impact to viewers' tolerance on brightness transitions, and also the light trend that maybe going to frames with small and bright highlights might be more tolerable. At the end, we wanted to validate these observations using actual content. So in this one, we changed the test frames with actual images, and we try to cover as many cases as possible when it comes to the position of highlights, the size of highlights, the bright areas. So as an example, you see that the highlight here is in the middle. Here, the highlight is on the edges. Here, we have a wide area, wide, bright area. So we wanted to cover as many cases as possible. Of course, the reference frame, they remained the same as before with the 3 fall values. And here we see an example of the test frame. And also an example with the same test frame processed to have a different combination of peak and fall value. Yes, as before, this processing, it created a really high contrast inequality that might affect the result. Here are the results when the fall value of the reference frame is equal to 0.1 candela per square meter, and the same way of presenting as on the previous experiment. What we see here is the same results as the noise. Light distribution seems to have no impact on viewers' tolerance. Again, it's a really slight trend in some of the cases, and these results are also the same, similar, because the actual tolerance level are not the same, but they have a similar picture when we raise the fall level of the reference to 1 and to 10. So in this experiment validates all the observations that the variation of fall value has the greatest impact on viewers' tolerance in brightness transitions. Yes, we do see a slight trend that transitions to frames with small and bright highlights might be more tolerable or less annoying, but we have to study further. Summary and conclusion of the whole work. So in this one, we assessed viewers' tolerance in temporal brightness transition in a cinema environment. We conducted 4 different subjective experiments where we studied the impact of the variation of fall, distribution of light, peak luminance, as well as color. We can say that viewers, they saw a similar tolerance to brightness transition for color and white. Especially, we believe that colors, the results show actually that colors, they have an independent impact on, they have an independent impact in visual discomfort, even in the case that only one group of cones blitzes is enough to cause visual discomfort. And we also found out that the variation of fall has the greatest impact, not the construction of the image, not the peak luminance, not the distribution of the light, not the contrast, of course. On this note, our results, they show that viewers, they reported slightly annoying transitions from 0.101 to 35, and from 10 to 75 candelas per square meter, and as annoying transitions from 0.1 and 1 to 75, as well as from 10 to 130 candelas per square meter. However, keep in mind that in this experiment, the lowest that we could go was 0.1. So, but in the upcoming cinema technologies, displaying technology, we believe that it's going to go way lower. So this 35 here should go lower as well. So as an overall conclusion of the whole work is displaying technologies that they can reproduce fall level greater than the today's cinema, today's projection. They can cause visual discomfort if, like, we mistreated them. And the results of this study, they can be used by display manufacturers to find the sweet spot between full screen white capabilities and cost. And finally, we can also use the results to implement warning mechanism for creators to warn them that, okay, this brightness transition, it might lead to visual discomfort, and let them make the decision, because it's their decision on the very end of the day. Thank you.
Thank you so much, Stelios. Great presentation. All right, once again, if anyone has any questions, pop up to the microphone right there. Oh, I was excited. A couple people stood up, but, oh, here we come, coming towards us instead of leaving.
Hi, CJ Flynn, Cinema Test Tools. I wondered if you can be clear, even though the eye can not get annoyed, we still might not have the full benefit of contrast if we have a piece of white up here and dark here or something like that. We may lose the ability to see the depth of the contrast, or...
Yes.
Okay. Just wanted to make sure there's no correlation there.
No, it's not correlation, but yes, like our eyes, they have some limitation on how much contrast they perceive at the same time.
So artists have to be aware of that. It's not just the pain involved, it's...
This is only for this study was only for the pain, or when, but yes, I really believe that.
Thank you.
Hi, Catherine Menninger, Portrait Displays. I had a question. to me, it kind of followed and made sense that as we adapted to a higher luminance, that our discomfort to a then higher luminance after that would decrease. So I was curious if you went back and kind of referenced your results to see how did the pain relate to how much out of that dynamic range that the eye can adapt to, like where that fell into that visual theory.
So, okay, yes, like by raising the reference, we also raising the threshold, but at some point we get some limitations because of the contours of the environment, and this has been validated not only from us, but some of the studies on the background, they reported exactly the same thing. So it's not exactly 100% clear, but at some point we start hitting the pain because it's really high contours with the environment.
Okay, so if I understood correctly, you couldn't find necessarily like, so like if I were trying to create like a predictive software or something like you were mentioning to say like, hey, warning, this could happen. There wasn't necessarily a connection to like, okay, well, if we're adapted at this low luminance range, at what point on the outside of that was that getting more painful? Does that make sense?
Are you talking about Weber's law?
Well, similarly, yeah. I'm just.
Oh, it's like to derive a function that has an input.
Well, I was just curious, yeah, if you had gone back, or if you think that that is an option as a resource to use in using this information, because as I was saying, like to me, it makes sense when I'm thinking of that theory. Well, so yeah, if we're adapted at a 0.1 luminance, and then you show me 50 candelas, there might be some level of discomfort, and then as I go to, if I get adapted to 10, then my discomfort's going to decrease, but that's also because my adaptation has shifted closer to that.
Yeah.
Have you looked, perhaps building off of that, have you looked back and started hypothesizing potential formulas for warning systems and such?
We have to, like at some point, yes, but like we don't have like all the data, but we know that at some point, everybody that wants to use the data is free, and go ahead and derive this formula.
Fantastic. Any more questions? Yes. And just point it that way since there's another one there.
That's good. Okay. Maybe a hypothesis and a question. The reason you're getting similar results for the fall is because, in theory, since you have a very wide screen, it's the same amount of energy that gets to your eye. Whether it is spread or not, it's what gets into your eye. So higher candela per square meter on smaller square meter is less energy than smaller candela per square meter on a big screen. The question is, have you gone to the step of trying actual moving imaging sequences instead of still images to factor in the fact that the eye is going to travel all over the screen, not just a still?
Thank you. First of all, this is the continuation step of this research. So yes, we're thinking of doing further and also implementing, assessing what are levels on an actual cinematic content.
Great. Thank you so much once again, Stelios.
Thank you.